Today we're going to talk about the properties of logarithms, and these properties are very important for calculus. There are 4 of them that we're going to discuss today. The first is called change of base, and it says that log base b of a is equivalent to log base 10 of a divided by log base 10 of b. Why would you want to use this? Well, if you look at your calculator, you'll notice that it does base 10 logs, because that's your log key, and it's associated with its inverse 10 to the x, and it does natural logs. It doesn't do base 3 logs, or base 5 logs, or base 7 logs. So if I wanted to use my calculator to find a log that I don't know, it would have to be that I could write it as a base 10 problem or a natural log problem. So just to give you a sense of when you would want this, log base 3 of 9 is 2. We know that because 3 squared is 9. And log base 3 of 27 is 3, because 3 to the third is 27. But what if someone asked me for log base 3 of 12? The best I could tell them is it's between 2 and 3, because log base 3 of 9 is 2, and log base 3 of 27 is 3, and log base 3 of 12 is somewhere in between there. Okay, so if I actually want to know what that value is, I could use my calculator and do log base 10 of 12 divided by log base 10 of 3. And if I use my calculator, log base 10 of 12 divided by log base 10 of 3. And I get approximately 2.262. Approximately 2.262. Again, I'm showing it is definitely between 2 and 3, and closer to 2 than to 3. Okay. And suppose I wanted to find something else, like log base 7 of 14. Well, wouldn't that be great if it were 2? But 7 times 2 is 14. But 7 to some power isn't 14. I do know that it's more than 1 and less than 2, because log base 7 of 7 is 1, and log base 7 of 49 is 2. So it's somewhere between 1 and 2. I could do that if I didn't have a calculator. That's the best I could tell someone. But if I do have a calculator available, I can do this as base 10 log of 14 divided by the base 10 log of 7. So base 10 log of 14 divided by base 10 log of 7. And that gives me about 1.356. Approximately 1.356. Okay, and why does this work? Well, let's take a base 3 log. So if I wanted a base 3 log, so log base 3 of x, and I use change of base, it would say log base 10 of x divided by log base 10 of 3. Essentially, that's like saying 1 over log base 10 of 3 multiplied by the log base 10 of x. And so what we're saying is that that's going to be a number, right? It's going to be a scale factor on the graph of log base 10 of x. So if I were trying to find base 3 logs, base 3 logs. That's the one in blue. And I could use the graph of base 10 log and scale it by 1 divided by log base 10 of 3. So I could stretch it in some ways to make it look like a base 3 log. If I were doing log base 7 of something, then that's base 10 log of, oops, let's try that again. If I were trying to do log base 7 of something, I could write that as base 10 log of that something divided by the base 10 log of 7. And again, what I'm doing is I'm scaling my base 10 log by some scale factor to make its values equal my base 7 log. Okay, so that's the why of it, but more importantly, you want to be able to do the how of it. Okay. My other properties have to do with expanding and condensing. So one of my properties is that log base b of the quantity u times v is equal to log base b of u plus log base b of v. So essentially, the log of a product is equal to the sum of the individual logs, given that we keep the base the same. And we're actually going to prove this. Okay, so I'm going to start on the right-hand side. Log base b of u, let's say that equals x, and log base b of v, let's say that equals y. And this I'm going to do is change to exponential form. So this means b to the x is equal to u, and b to the y is equal to v. So let's multiply these two. So b to the x, b to the y must be equal to u times v, right? Because multiply my left sides, multiply my right sides. Well, I know that b to the x times b to the y, when the base is the same, I add my exponents. So that would be b to the x plus y is equal to u times v. Now what I'm going to do is I'm going to change back to log form. So log base b of the quantity u times v must be equal to x plus y. But x is log base b of u. And y is log base b of v. So what I've got is log base b of the quantity u times v is equal to log base b of u plus log base b of v. So I'm anchoring my proof in the laws of exponents because a logarithm is an exponent. We have two other laws. Log base b of u divided by v is equal to log base b of u minus log base b of v. And log base b of u raised to some power is the same as n times log base b of u. Some people show this as the exponent comes out in front. And we have sort of seen this. I've run this through some problems like log base 7 of 7 to the 5th. It's like, well, what would that be? And when we did this, we said, well, that's x, and so 7 to the x is 7 to the 5th, so x must be 5. But now what we're going to be able to say is log base 7 of 7 to the 5th, that exponent could come in front, that's the same as 5 log base 7 of 7. Well, I know what log base 7 of 7 is. 7 raised to the first power is 7. So this is essentially 5 times 1, which is 5. Okay, so this property is syncing up with something that we have used before. Okay, so let's see how these properties come into play. Sometimes we're asked, or it becomes necessary in calculus, to expand an expression in order to make the individual work easier. So if we were going to expand this is a product, so we can actually expand this into a three-part sum. It's a three-part product, so it's going to be a three-part sum. Log base 4 of 4 plus log base 4 of x cubed plus log base 4 of y. And then this term is actually done. There's nothing else I can do with that. But this particular term, log base 4 of 4, is 1. I know that. Plus this term, I've got a power that I can pull out in front. So 3 log base 4 of x plus log base 4 of y. That's expanded in and is now as simple as it can be in an expanded form. Natural log of the square root of 3x minus 5 over e squared. That's a quotient, so I can expand that as natural log of the square root of 3x minus 5 minus natural log of e squared. Let's take the easier part first. That square could come out in front. So I would have natural log of the square root of 3x minus 5 minus 2 natural log of e. But the natural log of e is 1. So this is 2 times 1. This is 2. And the square root is actually the 1/2 power. So this is essentially 3x minus 5 to the 1/2 power. So I can bring that 1/2 in front and have natural log of 3x minus 5. There's nothing else I can do with this because the natural log of a difference is done. So that's as simple as these two can be in an expanded form. What if the easier thing to do is to look at a condensed form? And so we're going to try to pull things together. And we will need this tomorrow because solving an equation, the easiest way to solve an equation is with a condensed logarithm. So let's condense this. So the first thing I'm going to do is I'm going to bring that coefficient back in as a power. And that coefficient back in as a power. So log base 2 of the square root of x plus log base 2 of x squared plus 1 quantity cubed. Now I have a sum, so I could condense that into a product. Log base 2 of the square root of x multiplied by x squared plus 1 cubed. And you might say, wow, that's ugly. And indeed, it does look ugly, but maybe in a particular problem, that's the best way to go. This, I don't have any coefficients, so nothing's coming in as a power. I have a difference here, so I'm going to condense that. Log base 3 of x plus 5 over x squared plus 3x minus 10. And I'd love to be done, except now that I've got these together in a quotient, I can see that I might be able to do some simplifying. So log base 3 of x plus 5 over x plus 5 times x minus 2. And my x plus 5s are going to cancel. So I've got log base 3 of 1 over x minus 2. And for those of you who are processing restrictions, x cannot be negative 5. Okay? X probably couldn't be negative 5 anyway, because it's not in the domain of the log that we have. We actually have a very restricted domain here. Okay, so what if we had some problems with numbers and someone said, you don't get to use a calculator. You just have to do the best you can. Well, I might look at log base 7 of 98 and throw up my hands in despair. Someone else might look at it and say, oh, that's log base 7 of 2 times 49, which means it's log base 7 of 2 plus log base 7 of 49. And why would I want log base 7 of 49? Well, log base 7 of 49 is 2. So I have made this better. The only part I don't know is log base 7 of 2. Log base 3 of 45, no clue. Minus log base 3 of 5, no clue. However, it's a difference. So maybe if I condense this as log base 3 of 45 over 5, that's log base 3 of 9. Okay, we know that log base 3 of 9 is 2. So this problem, completely solvable without a calculator. Okay, so you may need to rewatch this. You may need to go back to your Algebra 2 notes on expanding and condensing. But please come to class tomorrow ready to use the properties of logarithms.